volcanoes can remain silent for hundreds, sometimes even thousands of years. Then, seemingly without warning, they can unleash rivers of lava, towering ash clouds, and explosions powerful enough to reshape entire landscapes. Throughout history, volcanic eruptions have destroyed cities and altered climates. But what exactly causes a volcano to erupt? To answer that question, we need to journey deep beneath Earth's surface into a hidden world of molten rock, immense pressure, and powerful geological forces. Far below mountains, forests, deserts, and oceans, our planet is constantly changing. Although the ground beneath our feet appears stable, Earth is actually a dynamic planet whose interior is always in motion. Most volcanoes are connected to tectonic plate boundaries. Earth's outer shell is divided into massive sections called tectonic plates that slowly move across the surface. In many regions, an oceanic plate collides with and sinks beneath another plate in a process known as subduction. As the descending plate moves deeper into the mantle, it carries water trapped within rocks and sediments. This water plays a critical role in volcanic activity. When it enters the hot mantle, it lowers the melting point of surrounding rock, allowing molten material called magma to form. This process creates underground reservoirs of magma beneath volcanic regions. However, creating magma is only the beginning. Most magma never reaches the surface. Instead, it collects in underground reservoirs known as magma chambers. These chambers can remain stable for centuries without erupting. Whether magma remains trapped or eventually erupts depends on a delicate balance between three important forces: lithostatic pressure, magmastatic pressure, and rock strength. Lithostatic pressure is the downward force created by the enormous weight of the rock above a magma chamber. Imagine placing a heavy lid on a pressure cooker. The thicker and heavier the rock above, the more difficult it becomes for magma to rise. Opposing this force is magmastatic pressure. This is the upward pressure generated by the magma itself. Because magma is generally less dense than the surrounding rock, it naturally wants to move upward toward the surface. Hot magma increases this upward force. The third factor is rock strength. The surrounding rock acts as a natural barrier, resisting the pressure from below. Even when magma pushes upward, strong rock can keep it trapped underground. As long as these three forces remain balanced, a volcano stays dormant. But if that balance changes, an eruption can begin. One of the most common eruption triggers starts within the magma itself. Magma contains dissolved gases such as water vapor, carbon dioxide, and sulfur compounds. Under high pressure, these gases remain mixed within the molten rock. But when conditions change, they begin separating from the magma and forming bubbles. Initially, these bubbles are microscopic. As more gas escapes from the magma, they become larger and more numerous. Eventually, millions of bubbles may fill a magma chamber, dramatically changing the behavior of the magma. A useful comparison is a shaken bottle of soda. Inside the bottle, gas remains dissolved because of pressure. Once the bottle is opened, the pressure decreases and bubbles rapidly expand. The same principle occurs within magma chambers. As volcanic gas bubbles grow, they reduce the density of the magma, making it more buoyant. This increases the upward magmastatic pressure. The more bubbles that form, the stronger the force pushing against the surrounding rock. Over time, this pressure can exceed the strength of the crust above. Small weaknesses within the rock begin expanding. Stress accumulates throughout the volcanic system, and fractures start to form. These fractures act as pathways, that allow magma to migrate upward. As magma rises closer to the surface, the surrounding pressure decreases even further. This causes gas bubbles to expand more rapidly, generating even more pressure. The result is a powerful feedback loop that can quickly accelerate toward an eruption. A remarkable example occurred in Mexico in 1943. A farmer named Dionisio Pulido noticed strange cracks appearing in his cornfield. Within hours, gas, ash, and volcanic rocks were erupting from the ground. The new volcano, known as Paricutin, grew rapidly and continued erupting for years. Scientists were able to study its formation. However, increasing pressure underground is not the only way eruptions occur. Sometimes the trigger comes from above. Landslides, erosion, and even the melting of massive glaciers can remove large amounts of material from the Earth's surface. Scientists refer to this process as unloading. When weight is removed from above a magma chamber, lithostatic pressure decreases. In effect, nature loosens the lid that was helping keep the magma contained. With less pressure pressing downward, magma may rise more easily and trigger an eruption. The surrounding rock can also weaken over time. Hot acidic gases escaping from magma can chemically alter strong rock into softer clay-like material through a process called hydrothermal alteration. As the rock weakens, it becomes less capable of resisting volcanic pressure. Earthquakes can produce similar effects. By creating cracks and fractures within the crust, tectonic activity can open new pathways for magma to travel. Seismic activity can also help trigger eruptions. Because volcanic eruptions can be extremely dangerous, scientists continuously monitor active volcanoes around the world. Thermal imaging identifies unusual heat patterns that may indicate rising magma. Gas sensors analyze volcanic emissions, while satellites and laser-based instruments measure tiny changes in the ground caused by moving magma deep below. Despite these advances, predicting eruptions remains incredibly difficult. Much of the activity occurs kilometers beneath the surface, where direct observation is impossible. Scientists can identify warning signs, but predicting exactly when an eruption will occur remains extremely difficult. Ultimately, volcanoes erupt when the balance between pressure and resistance finally breaks. Magma pressure becomes stronger than the forces holding it back, allowing molten rock, gas, and ash to escape to the surface. This ongoing battle between magma, gravity, and rock strength has shaped our planet for millions of years. It has built mountains, created islands, enriched soils, and transformed landscapes across the globe. And even today, deep beneath our feet, that battle continues.
Want more easy-to-understand science and educational content like this? Log into the Servly app and explore a growing library of informative videos designed to help you learn something new every day.